Did you guys have fun with that at home? It's impossible. Here's what I wanted you to do. I wanted you to take that to there. All right, so a whole bunch of reactions. First thing you do is H2 and Linlars. That'd give you the propene, and then HBr, sorry. HBr, peroxides, heat. Do an anti-Markovnikov addition. And then, but you're gonna end up with one too many carbons, and there's no way around this. So then do an alkylation. Then do an alkylation with that bromide. So what's the product of that? Stop just giving you everything. Your synthesis isn't going to work out, but okay, so the product of this, NH2 minus is going to pull a proton off there. You'll get the anion, and then this will do an SN2, and you'll get that. Yeah, no, this worked out. Right? Hang on a second. All right, we start with 3 carbons, reduce to the alkene, you get 3-carbon alkene, anti-Markovnikov, you get propyl bromide, 3 carbons, alkylate, 3 carbons. All right, so now I'm going to number these carbons. 1, 2, 3, 4, 5, 6. All right, now can you get from there to the product? Yeah.
That's how I drew it as well. Is that how you properly draw it? So I feel like in my head, when I just kind of see it to the 3rd carbon at the end of the triple bond, and for some reason I see it as a line going down.
So, broadly speaking, that's good that we draw organic compounds with this zigzag, but that fits the bond angle for an alkene. Right, that winds up giving you a 120-degree bond angle if you draw that zigzag like here, like if I drew another line here. And it draws the anti-configuration for an alkane. But carbon 2 and carbon 3 are both sp hybridized, so they're linear. And so just, they're aligned, yeah. Okay, so you definitely can go from here to the product if you treat this alkyne with ozone, right? You carve through these, all 3 of the bonds, you're going to get acetic acid, and then you're going to get butyric acid. You faked me out. I was, like I said, I didn't bring my stupid notes, so I'm sitting here and I was worried that you were going to be off a carbon, and I convinced myself looking at it, you were going to be off a carbon.
I was trying to do it backwards, and so
Yeah.
I assume that you would do like ozonolysis, but then you had that, you would have to have like a kind of big alkene, or alkyne. I have no idea how to get there.
So this step was, yeah. So but I was thinking when you did that, you were going to add 2 carbons instead of 1. So again, this is and you're going to have to use it again over there. Okay. So the one I invented on the fly, that turns out not to have been necessary, maybe, borrows a lot from this side. So go ahead and work the one now on the left. You can look at this one as much as you want, but I'm gonna walk through this again one more time. So working it backwards. This semester, the only way you guys know to make a carboxylic acid is by ozonolysis of an alkene, or an alkyne, sorry. Okay, so like I said, you've got a little bit of an advantage. You've got the disadvantage that you're doing all this for the first time. The advantage you have is there's not a huge number of reactions I can ask you, right? I've got volumes of reaction books in my office that are 6 inches thick. They're millions of organic reactions. So the only way you know to make that product is ozonizing an alkyne. And so, like you said, you've got to add carbons here. So we've got a 3-carbon group. We need a 4-carbon group. So you've got to add at least 1 carbon. And I think at this point the only way you guys know to make a carbon-carbon bond is an alkyne anion doing SN2 on an alkyl halide. That builds up a longer chain, and then you can do more stuff with it. You had a question?
Which one's the starting product on this one?
So yeah, here's another way to draw this. Start, finish, and then what a series of reactions like that means is there's more than one step, right? If that was if it was a single arrow, I'd be saying there's a reaction that does this. This is not saying there are 3 reactions. This is saying there's more than 1 reaction. Could be 2, could be 17. And my psyching myself out here, like count your carbons. That's going to be an easy place to go astray. All right, so on the one on the left now, what's this functional group? It's an epoxide. How do you make an epoxide? It's the first step of anti-dihydroxylation. All right, so it's just MCPBA that does that. So working backwards, you get this. So if I take this transalkene, treat it with MCPBA, I get the right epoxide. So now you got to figure out how to make the transalkene. So what reactions do you guys know that would make a transalkene?
The one with sodium and NH2.
What other reactions? I erased it. Like we can go back, you're just making an alkene, so an elimination would work. Right? This could easily be just an elimination. And the reason I put that up there is not, so you're right, sodium and ammonia, I don't want you to think, like that will make a trans alkene from an alkyne, and you know you got an alkyne in this reaction. So you know sort of probably that sodium and ammonia reaction, but if you're working this in real life, and you don't really know where you're going back to, like an elimination would do that. So if all I got to do is make that last product, if it turns out like I've got, you know, this bromide in lab or something, cool, I'm basically there. All right, so you could go backwards to a leaving group and some sort of elimination, or you could work this backwards to the same alkyne we made over there, right? And then the forward reaction will be sodium and ammonia. Right? So an alkyne, over on the right there, I show a reduction of an alkyne with hydrogen and Lindlar's catalyst. That will stop at the alkene. It'll give you a cis-alkene if there's stereochemistry, and the one on the right, there's not. If I have an alkyne and I reduce it with sodium and ammonia, I will still stop at an alkene, but it'll be trans. And so over here, we could have also done this. Right? This did not have to be H2 and Lindlar's. Okay. And so then we actually made this over on the other board. But again, I'll just go through it. This is going to be, first you're going to treat the alkyne, the terminal alkyne, with a really strong base. That'll make that alkyne anion. And then you're going to treat it with a primary alkyl halide, and that will do an SN2 reaction. So product of step 1 here is this anion, and then that does SN2. All right, so again, it's a 3-step synthesis. I don't mean to keep doing, syntheses don't have to be 3 steps. They can be 2, 4, 5, whatever.
Can you explain the SN2 reaction on this one?
On this SN2, not just
Not
SN2
general,
in
yeah.
general. Yeah, so I've seen a few confused looks. And this could be any terminal alkyne that's got a hydrogen out on the end bonded to the sp carbon. pKa here of this compound is about 25 because the anion that results will be in an sp orbital. It's got more s character, it's closer to the nucleus, it's more stable than an sp2 anion or an sp3 anion. It's still, 25 is a really low pK. I mean, this is not we would not call this an acid, right? If you spill this on you, it's not gonna ionize. But if you treat this with a strong enough base, and the classic is NH2 minus, but this can be any base whose conjugate acid is above 25. So we just do an acid base. So again, you're still going to have 3 carbons. That carbon out on the end is going to have a lone pair, be negatively charged. And now that's a super strong base, right? The conjugate acid has a pK of 25. I guess the other one, you also get ammonia. pKa of ammonia is 38. 38 is a lot higher than 25. Okay, so that carbanion, it's kind of bullet shaped, right? It's small. It's a really strong base. The electrons are right out ahead of the rest of the molecule, so there's no steric hindrance. And so if you treat this as a really strong base, it can do, you have to watch out for E2 elimination. Okay, so what you need here, I'll just draw what I've done. This has to be primary. Could also be methyl. But if the halide is secondary, well, obviously if it's tertiary, but if it's secondary, this will only do E2. Even if you use this would have to be cold. In the synthesis, I wouldn't require you to tell me that, but you'd want this to be cold. probably, you really don't have to give me this temperature, you can just say cold. Minus 78 is a really common cold temperature for organic chemists. So if I want to do a reaction at 0 degrees, if I want to maintain something at 0 degrees, I use an ice water bath. Right? Sort of by definition, if you have solid water and liquid water in equilibrium, the temperature of that bath is 0 degrees. Same principle, if I have dry ice and acetone in equilibrium, temperature is minus 78. So it's an easy temperature to access. So this is really cold, and now this just does the SN2, and that makes, so you've got a negatively charged carbon as the nucleophile, an sp3 carbon as the electrophile. So you make this carbon-carbon bond. And like I said, in Orgo 1, any problem where you see I've got like X number of carbons in my starting material, and I've got X plus something, I've got more carbons in my product, this is pretty much the only reaction you guys know that makes a carbon-carbon bond. Orgo 2 is full of them. Right? So I promise in the spring, if you take Amanda's, don't call her Amanda, I would call her Dr. Jones, but then it seems like I'm talking about myself. So Dr. Amanda Jones. If you take her class, you're going to do a lot of these synthesis problems, and you're going to make a lot of carbon-carbon bonds. So Orgo 2 looks at a bunch of reactions that make carbon-carbon bonds. And I think a lot of you started to do some chemistry that, you're sort of reverse hydrogenation. You wanted to do like an oxidation. Like there are better ways to do this reaction. There's really probably not a better way to do the one over on the left. But this SN2 reaction. So 2 things you pick up today. If you guys see a synthesis where you've got to add carbons, it's pretty much got to be this alkylation of an alkyne carbanion. What was the other one? If you start with an alkane, pretty much the only way to do that is by doing a radical halogenation. Questions? All right, that's it. Say goodbye to Kirby 010. This is your last, well, it may not be your last class here. It is probably my last class here. So I'll see you guys in Salem on Friday. And then the exam next week is also in Salem. Actually, come to think of it, that room is not available on Monday. I have to figure out, I'll let you know where the exam will be on Monday. Probably be in our labs, in the labs.
Oh, sorry, I'll let you stop that.
Yeah, just let me stop it.
Yeah.
You want to record this conversation? You can always record it.